Hello everyone and welcome to another data recovery session. Today I'd like to talk about table doesn't exist error. As always, my goal isn't just give you a step-by-step how-to, but rather educate you on a topic so you feel confident fixing the problem, even if something doesn't go exactly how the internet says. So, a plan for the video. To explain where the error comes from, I'll dive a little bit into InnoDB internals and review some scenarios where the error happens. Then, I'll outline a few recovery strategies. For each of them, I'll explain pros and cons. And finally, I will show how to fix the error with undrop for InnoDB toolkit. If that sounds good, let's get to it then. Let's say we have a MySQL instance, MySQLD. MySQLD. It uses files from MySQL data directory, which is for short I will call datadir or MySQL datadir. For Linux it's var lib MySQL and inside this data directory InnoDB creates system tablespace ibdata1. ibdata1. Inside this system data space, InnoDB keeps information necessary for it to function properly. And one of big components in this system table space is InnoDB dictionary. InnoDB dictionary is a set of InnoDB tables. Normally they are not visible for a user. Actually, in early days of InnoDB you couldn't see them at all. Later on Percona added them to informational schema for read-only access, and after that Oracle included that into the upstream version of MySQL. So today we can see those tables in informational schema, and they usually called with sys prefix. Here's some of them. List of tables we can find in sys tables. As the name says, this table contains list of tables in InnoDB. Systables has several fields that are interesting for us. Well, first of all, it's a table ID. Table ID. This is auto-incrementing integer. Then name. It's a table name, but it has a special format. It's a database name / table name. For sake of example, let's say for Sakila database table actor, name will look like this. There are some other columns. For context of this video, important column is space. It's also an integer, it's also incrementing integer. It actually means where indexes of this table are stored, in what table space. 0 stands for ibdata1. Remember, InnoDB used to store user tables in ibdata1. Today we have an option to control where InnoDB creates user table spaces. If InnoDB file per table is off, then tables will be stored in ibdata1. If InnoDB file per table is on, which is default since version 5.6, then for each table InnoDB will create a separate table space, and it will be stored in a file with extension IBD. Again, for example, if we have a Sakila actor table, there will be directory Sakila / actor IBD plus MySQL specific file is a file with the structure actor frm. Actor frm. Now, when we create a table in InnoDB, InnoDB adds a record to systables. So, table ID, name. Here take some free number, 11 for example. Then again, Sakila / actor, and then space, type space. For the space number, it picks next available number. For example, 20. There are other tables in the dictionary, and InnoDB stores them. InnoDB uses them to store other information about the table. For example, sys indexes stores a list of indexes in a table. First of all, every InnoDB table needs to have a primary index. If a user doesn't define the primary index, then InnoDB will use either unique index or will generate a 6-byte integer field and will use it as a primary index. Plus, user may define secondary indexes in a table. All of them will be listed in sysindexes. There are other tables like sys column. This table lists fields for a table, and sys fields. This table lists fields for each particular index. So all of these are available in informational schema. There are other tables in the dictionary as well. For example, there is a table for foreign keys and others. I will not cover them in this video. When we need to execute select stuff from a table, when we need to read records from a table, here's what happens. InnoDB takes table name and from systables gets table ID. From the table ID, it finds the primary index. For the primary index, it gets root page ID. Remember, index in InnoDB is a B+3. It is a B+3, and to read records, you need to start with the root page. Here we get it. Then, for each table by table ID, well, not for each table, for this particular table we are looking for, we get list of columns and their types, because we need to know what type we read from InnoDB page. And then as soon as we have all this information, we can take an InnoDB page and read records from them from it and return to a client. InnoDB gets table ID by its name from systables. And we remember that it's create table that adds records to systables. And if there was no create table, then bam! This request fails, and we get table does not exist. And that's why it happens. Why there wouldn't be a record in InnoDB dictionary? A typical situation happens when you have Sakila database, Sakila directory, and you take FRM and actor IBD files from some other server and copy them inside Sakila directory. You did copy actor FRM file, and that's why MySQL sees the file and believes it's a table, but InnoDB doesn't have a record in systables about this table. So every time you try to access the table, InnoDB cannot find it in the dictionary, and sorry, table doesn't exist. Another possible situation when the dictionary may be lost is when the original IB data file is gone. For whatever reason. Maybe it was deleted by mistake, or maybe it's some file system corruption. So if there is no IB data file inside MySQL data dir, then InnoDB does what? It just creates a new one, and the new one is empty one. And even though you have the original IBD and FRM files in the database directory, IBData1 and dictionary inside this file doesn't have any record about these tables. And again, any request to any of those tables will lead to table doesn't exist error. Now, you may ask, how come it works for MyXAM? You can copy MyXAM files, MYD and MYI and FRM file. You can drop it in a database directory, and MySQL will pick them up and will be able to successfully read records from those tables. And I believe there are a couple of reasons. First of all, it should be noted that InnoDB used to be a separate product. It used to be a separate database, and it had nothing to do with MySQL itself. Later on, it became a storage engine for MySQL, and this is when it became so popular, but originally it was a separate product. And that led to, there were some design considerations, and they were still in place, and it wasn't realistic to redesign it from scratch just to plug into MySQL. Second reason is design of InnoDB itself. You remember, user data could be in the system table space, and if it's so, there should be some source of information. Where can I find root page of InnoDB index so I can traverse it to read records from it. Without a dictionary it wasn't possible. But now, yeah, sure. If you have actor FRM file separate, you can get all columns from it, all data types from it. If you have actor IBD file, yeah, you can easily find this table space. You don't need a dictionary for that. And with small maybe changes, you can put the root page as some fixed place in the table space. So that problem is also solvable. So it's a little bit of legacy plus, I don't know, tradition, and here we are. We do need InnoDB dictionary to find indexes and root pages in InnoDB table spaces. Now I would like to show how table looks like inside InnoDB dictionary and what happens when you create the table, how it's represented in the dictionary itself. For that I prepared some data directories that you can see here. Empty directory. This is a initialized MySQL data directory without any tables. This is a data directory with just Sakila database, and this will be our working directory. I will start with the empty one. Okay, and I will create a Docker container on this data dir. So we will run container named MySQL. I will mount some volumes. Well, first of all, data directory, data dir demo, that will be mounted to var lib MySQL. Another volume to share data between the host machine, which is my laptop, and the container itself, just for convenience. Let's mount it on /share. Alright, what else we need? Remove the container when it stops, and tag, which will be, we will use MySQL 5.7. Okay. It's starting, initializes the database, starts, everything looks good. Alright, now to connect to this container, we run exec -it MySQL and shell bash -l. Oops, typo. Alright, now it's better. Now I can connect to MySQL instance here. If you look, there are no databases except like default ones. Alright, let's create the Sakila database. Create. Oh, I will start with showing InnoDB dictionary. Originally, it wasn't accessible for a user. It was hidden inside InnoDB, and the user couldn't query records from these tables. User couldn't see those tables at all, so it was totally invisible. And then somewhere in version 5.5, I believe, or maybe even 5.1, Percona exposed these tables in informational schema, and later on it was included in upstream, so that way DBAs can get more insights of what's going on, including getting data to to fix this table doesn't exist problem. All right, so let's use information schema. Information. All right, show tables, lots of them. We are interested in tables that contain sys in it. So not all of these are dictionary tables. Some of them are derived from dictionary tables. Nonetheless, this is sys tables. It's a list of InnoDB tables. Select star from, nope, from sys tables. Okay. Okay. Let's show only one record. All right. Some table ID 14, called sys data files. By the way, it doesn't include the database name because, well, it's not a user table. As opposite to, for example, sysconfig. Let's use that one as example, where table ID equals 39. All right, so here we have table ID, name, some flags, number of columns, space ID, and some additional information. File format, row format, page size if the table is compressed, and space type single. No idea what it means. All right, and of course there are no table names like Sakila, where name like Sakila. All right, now let's create database Sakila. Create database Sakila. All right, still no names because we don't have tables in it. All right, now let's create some tables in database Sakila. I will connect another I will connect another session. Oops. All right, and in here I have some table structures for Sakila database. Okay. Sakila actor, let's create it. Now, what we see is a table was created, and InnoDB dictionary now contains a record about table Sakila actor. All right, what do we have here? Interesting enough, table space is 25, name 7 columns. By the way, 7 columns. Let's check it out. It has 3 columns, but in here it says 7. Why so? Let's see. Primary key, first name, and last timestamp. I can explain why it would contain 6 columns, 4 user columns, and plus 2 additional columns, transaction ID and rollback pointer. All right, that's good to That's good to know. Let's check other tables. Let's check sys indexes. So we have sys indexes. And by the way, table name is 44. Select stuff from sys indexes where table ID, ID equals 44. There are two indexes. One is the primary, one is the secondary. Okay. What do we have here? Table ID, index type, number of fields in the index. Primary is just one column. It's okay. The root page, page number 3 inside the user table space, number 25. Merge threshold, don't know what it is. All right. Now let's check sys columns. We don't have a pager here, unfortunately. What we got here? 4 user records. It's still not clear why 7 records, 7 fields in this table. As I said, 4 user records, 4 user fields. One is transaction ID, one is rollback pointer. All right. Let's say it's a mystery. Show create table Sakila actor. Primary key is defined, so yeah, that's strange. Okay. Whatever. What else we've got in sys tables? That would be sys fields. But sys fields, it lists records in it lists fields in indexes, not in the table. For example, yeah, there is no table ID. For example, we have two indexes in table actor, right? The primary index and the secondary index. So let's see what fields are covered in this secondary index. So our index ID would be 42. So just last name. And 41 is just ID, actor ID. Okay. So here we go. InnoDB dictionary contains records about actor table, and we can, I don't know, we can query this table and we can work with it. Now let's reproduce table doesn't exist error, the main topic of this video. So I'm gonna kill this MySQL instance. It exits gracefully, but I want to start it with empty database again, with empty table space again. For that, I remove the data directory that we worked with, and I will take empty one again. Okay, it's up and running. Now, if I connect to this container again, and if I go to var_lib MySQL, I will see MySQL files here. There is ibdata1. There is no Sakila yet. Let's create database Sakila. Now we have Sakila directory. Inside this directory, there are no files except this one. But there are no user table files. Now, I have some crafted files, actor FRM and actor IBD from some, I don't know, some random MySQL instance. Not from this one, just some other instance. So if I copy these files from other instance, oops, okay, just 2 files, and if I connect to MySQL again, oops, what's wrong? Exec should be exec. Okay. MySQL Sakila. I will see the table actor, but if I try to query it, table doesn't exist. What happens? Well, exactly what it says. The table doesn't exist in InnoDB. If we query in InnoDB dictionary, information schema, show tables, select star from where name like Sakila, there are no tables in it. So this is what happens. There is no a record inside InnoDB dictionary about the table. So when MySQL tries to read records from this table, InnoDB responds to the MySQL server that, sorry, table doesn't exist. Also, I see that in the error message here, InnoDB prints that it cannot open table Sakila actor from the InnoDB dictionary, data dictionary through FRM file for the table exist. All right, so that's a problem, and let's see what we can do with it. Okay, now when I understand why the error appears, I can think about some strategies how to fix it. So a naive approach would be this. All right, the error happens because InnoDB expects a record in InnoDB dictionary, but the record doesn't exist, so we get error message, table doesn't exist. Let's create that record in systables then, or in all InnoDB dictionary tables. InnoDB doesn't allow you to create records in the dictionary tables directly. You cannot insert a record in systables. But if you create a table, InnoDB will create records in systables, sysindexes, and all other tables. So what we can do is we can run create table statement, create table table actor, and assuming that we specify table structure exactly the way it's supposed to be, this statement will create all necessary records inside the InnoDB dictionary so we can access the table. But right after create table, InnoDB will create empty tablespace actor IBD, which we don't need because it is empty, it doesn't contain any records. So what we're gonna do is we're gonna take our actor IBD from our old server that crashed or whatever, actor IBD with records, with user records, and we will replace it instead of this actor IBD. And let's say table structure matches, we have IBD file in exactly same format as InnoDB would expect it, and we can query the table and access our records. I call this a naive approach, and I know that it's not gonna work, and let's see what happens when we do so. Okay, the table doesn't exist. Simple copying files didn't work for us, so let's try to create a table and then replace actor IBD. So for that I will remove these files. So first I will create the table. Share and drop Sakila actor SQL MySQL. Okay. Oh, sorry, MySQL Sakila. So InnoDB doesn't allow us to create this table anyway. Let's do this. Let's flush tables. Flush tables. That will cause MySQL to close and reopen tables again. Now, okay, we created the table. Show tables. We have an actor, and now let's replace IBD file. So this is empty IBD file. Let's replace it with IBD file with data. So that would be share actor IBD. All right, and now let's query the table. Nothing happens. The table, well, in this particular case, actor IBD was still open by MySQL process, and it looks like MySQL still holds descriptor on this file. So let's do this. I will restart MySQL. Well, with container it means we need to restart the container, and let's start the container again. We already copied the IBD file to the destination inside the Sakila database. So let's start MySQL on that database. So what happened here is MySQL crashed. And why it crashed? Because tablespace ID is 25 in the data dictionary, but in the file it is 23. Oh, tablespace ID doesn't match. So what's going on here? We know that we already have a record in the dictionary, and this is what happened. What happens? This is what happens. We do have record in systables. So there's some table space ID. Oh, there is some table ID. Then Sakila actor. Then number of columns 7. Why? Then whatever, and then we have space. In that space 25 in the dictionary. In actor IBD, space ID is 23. So what's going on? What is 23, and where this 23 comes from? And the matter is, if we have IBD file, it consists of number of pages, right? And each page inside InnoDB, each page inside the table space contains information about space it belongs to. For example, somewhere in the header it has these 23. When InnoDB reads a record from the dictionary, it gets 25. Then it opens file actor IBD, reads table space from here, it sees 23. Doesn't match, and that's why InnoDB crashes. So where is the space ID inside InnoDB page? Here I have a format of the page header. Actually, it's a fill header. It's a even beginning of the file table space. And it's a little bit confusing, but here it is. Page space field used to be used for space ID, but in very old InnoDB version. Now these 4 bytes are used for InnoDB checksum, for the page checksum. And this field, it used to store some log number. I don't even know what it is, but after MySQL version 4.1, this field stores space ID. Okay, so let's take our page, let's take our actor IBD, and let's look inside what's in there. Actor IBD, oops, except I need binary editor, and offset is 22. 22 is a hex number, so 22 would be right here, 4 bytes, and we can see it's 17. Alright, 17 in hex corresponds to 23 in decimal. Bingo! Let's summarize the state of things. If we just copy actor IBD and actor FRM to fresh new InnoDB instance, then InnoDB cannot read it because there is no corresponding record in the dictionary. Okay, if we create a table, a fake table, empty table, actor, and then replace IBD file, we cannot even start MySQL because it crashes, and it crashes because space ID mismatches. In the dictionary we have some random number. In our example it's 25, but it can be anything. In the space ID in a page is 23, so there is mismatch. How can we fix this? So here's a couple of strategies. Strategy number one. It was described in a blog post by Chris Callender, I believe, a while ago. He suggested to fix space ID by creating a table. So let me explain. In this particular case, it's not gonna work, but the idea is following. Let's say instead of 23 here, we had some really big number, well, bigger than 25. Let's say 101, 101, 101. So what we can do, we can create this table 101 minus 25 times. What will happen is you create a table once, InnoDB picks space ID 25, you drop it, InnoDB removes this record. You create the table again, InnoDB adds a record to the systables, space ID will be next one, 26. You drop the table again, create again, 27, and so on and so forth until you get here 101. Then you can replace IBD, the original empty IBD file, with the actor IBD with user records, and then there will be no mismatch, and then InnoDB can read records from this table. I think it's obvious why this way doesn't always work. In our case, for example, space ID is 23. And we already have 25 in the dictionary. So there is no way we can go backwards. There is no way we can go backwards. Plus, if you have more than one table, these coordinations of IDs, when you cannot decrease them, it just kills whole idea. It works realistically for quite limited set of cases, but I like this approach because it's simple enough. You just create drop until two IDs match, and here you go. You connected the table. So that's way number one, strategy number one. Strategy number two is, what if we read space ID from the dictionary and update it here? So second strategy is to update page. It's a little bit tricky one, because what happens here now is you have to open IBD file, you have to find that place, remember offset 22. You have to update the number to match what's inside the dictionary, and then you have to save it. Now, it seems to me that InnoDB reads only the first page. It doesn't read space ID in every page, so you can get away with it. And that's not very clean way to update IBD file, so it's a little bit risky, and realistically it can be used only to start MySQL in read-only mode, read all records, and then kill MySQL instance and import those records into a fresh new MySQL instance that doesn't have any corruption, and good to go to production. Another problem with this is the page checksum. It has to be updated, because if you change this piece of data, of course the checksum changes and you need to update it accordingly. So that way is also not very reliable, and truth to be told, difficult. Third way, what if we don't update the original IBD file? What if we update the dictionary? What if we put 23 here instead of 25? It's also possible, and I actually wrote a tool to do that. It's called IBD Connect. You can still find it in Percona Data Recovery Toolkit. What this tool does, it reads space ID from IBD file, it updates, finds this record in the dictionary, it updates this space ID, and another tool in checksum changer, I believe, can calculate a new checksum for a page in IBData1 and update the checksum so it matches, it doesn't freak out InnoDB. So that's the third way. I would say it's equally risky as way number 2. Practically, it worked for me a couple times. I did extract records from IBD file in that way, but also true that I saw some MySQL crashes, because again something was still off in this setup, and InnoDB didn't like it, so it crashed. So what is the better way? There should be better way. And I believe that the best way to recover from this situation is to use Undrop for InnoDB toolkit, and particularly Stream Parser plus cparser tool. Let me explain. So that would be way number 5 or 4. Yeah, 4. cparser basically is a InnoDB reader. You give it a page, it reads records from this page, and it produces table dump. it ignores all information about page checksum, file space ID, all other fields. All cparser uses for its work is field names, their lengths, and it tries to read them. So we will take IBD file and with stream parser actor IBD. With stream parser, we will split this IBD file into InnoDB pages, and we will sort them by index ID. Remember, actor IBD, actor file, actor table actually has two indexes. One is the primary index and one is the secondary index. So stream parser will put these two different indexes into different directories, so it's easier for us to work with one index at the time. And then after we split IBD file with cparser, we will read records from the primary index, and we will get output like tab separated values format. So that would be actor ID, then first name John, last name Smith, and the rest of the fields. Why I think this method is the best? Because first of all, it's reliable. If you have IBD file and the IBD file is not corrupted, stream parser will read this file without any problems. If it is corrupted, cparser still can read this file. It can still extract as many records as possible. Probably you will need to tune some filters, but the bottom line is cparser will extract all possible records from actor IBD, which MySQL will not, because again, if InnoDB sees some inconsistencies, if some field is wrong, if the checksum is wrong, if next page ID is wrong, InnoDB will crash and you will not get your data back. Stream parser ignores those errors. All it does, it tries to read and to read InnoDB page and fetch as many records as possible. Second, this way is good because it allows to take a healthy MySQL instance and when you read records from actor IBD, you will get tab separated values dump. You can take that dump and you can import the values of the table directly into healthy MySQL instance. This is really good because you will save time. As soon as you finish uploading new records into the MySQL instance, the instance is ready to serve production traffic. It is not in an undocumented state when either IBD file is changed manually or actor IBD is changed manually. You know, those number 2 and number 3 options were still kind of hackish solution. It allowed to start MySQL in force recovery mode, but as a production database, it's not usable. It would crash all the time. The only way to recover from that situation is to extract records with MySQL dump, then kill the patched instance of MySQL, create a new one, brand new one, and import the table dump back into MySQL instance. With this method, we can start with a healthy MySQL instance right away, and as soon as we got the records, we upload them, and MySQL is ready to serve traffic. So we save one step, which can take significant time, especially when the table is huge enough. All right, so what else can I show you? Maybe I can show you how this works in action. At this point, we ended up with a MySQL instance that simply crashes. There is nothing we can do. Yeah, it reliably crashes. Let's recover from this state. So first thing I would like to do is I would try to remove this Sakila, this actor IBD file. So let's see if MySQL starts. Okay, MySQL starts, but we are in a kind of broken state because we do not have actor IBD. I want to drop this table, drop Sakila. I want to drop it to clean, because I want to clean InnoDB dictionary. Okay, it did let me drop the table, but let's see what's in the log. Oh, it says failed to find tablespace actor in cache. Good. It's a dictionary cache in memory. Attempting to load the table space with space ID 25. Okay. Operating system error number 2, which means no file found. So far everything is expected. Cannot find, la la la. Well, too bad, but we don't care. We cleaned the InnoDB dictionary, and we can start from fresh state. Show tables, nothing. All right. In the share directory, I have undrop for InnoDB here. So let me show you how to use it to recover records from this actor IBD file. Oh, Vim not found. What about? It works. All right, we do have records in this file, in actor IBD. So let's use undrop for InnoDB to extract those records. Okay, I see I compiled it already. If you need to know how to compile undrop for InnoDB, there is another video devoted to the compilation and usage process, so check it out. Now I will just use it. So I will run stream parser on the actor IBD file. Okay, the result of this command is this directory let's look inside. We have two subdirectories. One is field page index. These directories correspond to page type, and field page index is a type of page that used to store index pages where user data is stored. So let's go look inside it. There are two files here, and each of the files corresponds to InnoDB index. Table actor has two indexes. One is primary, one is secondary. So 41 is always primary. The lowest number is always the primary index, and all other numbers, these are secondary indexes. So we need this file because here we have our table, records of our table. Okay. Let's go back to our toolkit, and there is another tool, cparser. cparser accepts a file with InnoDB pages. It also requires table structure, and then it produces the table dump. So let's try to run it. cparser -f pages actor index 41. Table structure was somewhere in Sakila actor SQL. Okay, so let me quickly show this structure file so you get the idea what it should look like. So basically what we need is this create table statement. This create table statement defines fields and their types, and cparser parses this create table statement, and it reads information about the table, like what types, what fields we have, what types they are. So if we just run cparser, it will show us some records. Now this table dump is tab separated values dump. We don't have less. Okay, let's install it, get update, install less. These are two additional fields that I was talking about. This is transaction ID, this is rollback pointer, and this is just table name. These, starting from this integer, these are user fields, and those are actor ID, first name, last name, and some timestamp. I don't remember what exactly it is. Now, to load this file, cparser produces a helper command that we can use right away to import this table dump into a MySQL instance. But we need to make sure that the load data in file command can find the table dump in this file. So for that reason, let's write output to this file, and by the way, we will need to create a directory, dumps, default. Okay. Now, if we run this, the table dump will be stored in this file. Let's see. So this is the file, and the load data command is right here. So MySQL, Sakila, and load data local in file. Oh, table doesn't exist. Okay, that's a good point. Let's create it. And we already have the structure. By the way, if you need to recover the structure from a frame file, check out my other video about table structure recovery. Now we have actor file. Let's run the load data in file again. Voila! The table is loaded. We can query it. All fields are valid. The field was last update. All fields are valid, and what is good about this state is that as of right now we can use this MySQL instance in production, so it's ready to serve production user traffic. Alright, I believe that constitutes the topic that I wanted to cover today. I hope it was comprehensive enough, and I hope it wasn't boring enough. Well, sometimes it is boring, but yeah, I hope it helps, and don't forget to take backups. Take care.